Hi, I'm John Anderson, and this is enhanced content for Common Engineering and Technology Courses, Module 4. Today we're going to be talking about materials. I want to cover in this video three of the modules that are included in the Aerospace Manufacturing Education website under materials, and they are the history of aircraft materials, aerospace materials for failure modes, and aerospace materials quality control. In addition, I'm going to assign in the student activities uh, document for you to go and take a look at a couple of more modules that are in this same folder that aren't traditionally associated with materials, um, but I think that you'll find interesting and perhaps useful uh, in part or in whole in some of your engineering and technology courses. So let's get started. The history of aircraft materials is an interesting module. This module probably could be best used as an introduction to a materials course, a materials survey course, and perhaps even in a design course. It's roughly one lecture hour of materials for the PowerPoint. It has a very nice set of instructor notes with some test questions added into the instructor notes, and some student activities. So it's a nice complete 1 to 2 lecture hour segment. If you use 2 lecture hours, if you do some of the student activities in class, and maybe 1 lecture hour for just covering the PowerPoints. What this module does, and we'll kind of go through quickly some of the slides here. What this module does is it goes through and looks at the development of aircraft in conjunction with available materials. So materials were actually developed to meet the needs of this new aerospace industry. Starts out talking about rubber and vulcanization is necessary for seals and gaskets for motors, for instance. And then the first Wright brothers airplane, they overcame a series of issues that had to do with materials and the strength to weight relationship of materials in order to make this first airplane work. For instance, the aluminum engine block, they had to develop themselves. Nobody was making that. And so they came up with the engines at the time were cast iron blocks, and that was just not suitable in terms of weight for an aircraft. So they had to develop their own aluminum engine blocks, and that started aluminum down the commercial application road. The airframe was actually made of spruce and steel wire for reinforcement because those were available materials, and they were the best materials on the market that would allow them to build the airframe. They used a fabric skin because that was known technology in the day. The fabric skin was a cloth skin stretched over this wooden structure and then coated, or doped as the terminology went, coated with a material to make it non-porous, so it acted like a sail. And sails, of course, were familiar technology in this era. So this is one of the Wright brothers aluminum engines that they developed. Another important piece in the puzzle of making airplanes was the development of plastics. Plastics have this interesting feature in that you can mold it to near net shape. So you can have it as a liquid form, put it into a mold, solidify it, and it'll retain that shape of the that you molded it into. Um, in addition, plastics have interesting electrical properties. They have high resistance to electrical flow. So it became ideal and was used first for electrical components. This particular piece is part of a distributor for a motor. So you needed a structural part that wouldn't conduct electricity to hold the conducting metal parts together and in a certain place in space. So this is Bakelite. This is the first commercial plastic. It's a thermoset material. That is, once you solidify it in a mold, you can't reform it. There are two types of plastics, commercial plastics, thermosets and thermoplastics. Thermoplastics are characterized by their ability to be melted into a liquid form, molded, then and solidified, frozen in a solid form, then remelted and frozen into a different shape without losing the bulk material properties. Thermosets, on the other hand, you destroy them if you try to raise the temperature enough to melt them. They don't melt, they burn. So this is a thermoset material. That was the first commercial plastic. Thermoplastic materials at that time had very low melt temperatures and very low strength, and were just not suitable for structural applications. So this is the evolution of the airframe design from an all-metal steel tubing frame to a stressed skin construction. That is, the skin is taking part of the design loads, to a monocoque construction where you have a stressed skin that either takes part or all of the load. In the 30s, aluminum was actually discovered in the 1800s, but it wasn't until large-scale electrical power availability came to being that aluminum was possible to manufacture aluminum. So it didn't really start finding commercial application until until the 1930s, and then into World War II, the applications grew very rapidly. In 1936, plexiglass was commercialized in the aerospace industry. Plexiglass is a thermoplastic material, so it can be melted back down and reused. It has some interesting properties. It has very high strength, and it has a very high melt temperature, and it's optically clear. So it found use in applications such as cockpits, where you had to have a fairly high strength. It had to withstand aerodynamic forces and maintain its shape, and it had to be clear enough that the pilot could look through it. And then we get into the era of fiberglass. Interestingly, the technique of making glass fibers was developed in the United States, but the resin that holds these glass fibers in a certain shape was, although it was patented originally, the polyester resin was patented in the U.S. The Germans, prior to World War II, really did a lot of work on the manufacturing methods for the resin and in manufacturing composites. And the British spies stole the manufacturing methods from the Germans and gave them back to the U.S., and U.S. companies started making fiberglass components for airplanes. Development of super alloys for things like jet turbines, turbine blades, that sort of thing. The A-12 was the precursor to the SR-71 and a couple of other aircraft. It was a high-performance aircraft built by Lockheed Skunk Works for the CIA in the mid-60s, I think it was. Carbon fiber composites. Carbon fiber and fiberglass differ primarily in, of course, the fibers that they use and in the resin that holds them together. So fiberglass typically has a low, what we refer to as a low performance resin. The polyester resin has a fairly low melt temperature, doesn't operate well at high temperatures. The carbon fiber composites can be made with high performance resins that will give them advanced strength and thermal properties. And then continue on with the development of fiber composites. And we're going to talk more about fiber composites later in this course. We get into ceramics. For an example of this would be the Space Shuttle thermal protection tiles from the 80s. Aluminum lithium was developed in the late 90s. Lithium is the lightest metal around, so when you combine this with aluminum, you can end up with a very strong, very light metal. Continuing on with different types of fiber composites. And we get to the Boeing 787. Boeing 787 uses a lot of composites in their structure. So this is a fuselage section for a 787 that's a composite structure. We get into some really interesting stuff that's actually becoming reality. Embedded sensors and monitoring systems. The embedded sensors rather, in aerospace are reality right now, and this is becoming more commonplace, I think, in automotive also. But for health monitoring in composite structures, when they build a wing structure, for instance, they embed these sensors in it so that it can tell the maximum stress that's been put on that wing structure, and from that make some decisions about maintenance and replacement of parts. Another very interesting thing that's going on, there's a lot of research going on this, is for materials that actually change properties. You may have read about the electric muscle, where you put a current through a material and it contracts or expands. That type of thing. But when you apply this to aerospace, you start thinking in terms of eliminating discrete control surfaces like ailerons or rudders, flap systems, and replacing that with a lifting body or airfoil that actually warps itself and changes its lift characteristics. So, interestingly enough, this is how the Wright brothers steered their airplane back in the early 1900s. They actually pulled on cables and warped the wings to give an increased or decreased lift and to turn it. And so now that's possible to do uh, with electric controls that would modify the structure of the wing, or the shape of the wings. So let's take a look at the instructor notes real quickly for the history of aircraft materials. Um, this is a suggested schedule. If you're going to do this as one class, you could do just the presentation and the pretest in 50 minutes. You could actually, I think the presentation could be expanded to fill 50 minutes easily. Class 2, you could also do a review, student activities, and a post-test. So let's take a look at those materials. Like the other modules we've talked about, each slide has its own description with interesting little things that you can talk about on that particular slide. Going down to the bottom, so we page through this. We'll find student activities. So there's a couple of student activities in here, and I will probably give you a couple of those to work on for your student activities for this C2 Gen course. And we have a pre and post test for the materials in this module. So you can integrate that into your testing or use it as is. References. So these are websites that you can go to get more information on the individual topics that we talked about here. Okay, so that ends the history of aircraft materials. The aerospace materials failure modes is one of my favorite modules. So in this, the interesting thing, the most interesting use of this module that I see in the broader context of engineering and technology courses is to give students in machine design courses, and perhaps in materials courses also, an overview or a mental picture of what the consequences of inadequate design are. So you can consider this the scared straight equivalent for engineering students. In any event, it's also fairly graphic, and it's easy to visualize, and I think it helps put the theory of machine design into context. So this goes through and talks about different failure modes. Why are we focusing on failure? Well, in aerospace, for instance, the results of failure can be catastrophic in loss of life and property. Moreover, it's interesting to use the philosophy of designing to prevent failure. So anyway, this starts out and talks about the different types of materials that are used in aerospace structures, because that's the example that we want to use here. How do materials fail? A listing of failure mechanisms. Some interesting graphics here. This is the Airbus A380 wing deflection simulation, and we use this to talk about elastic versus plastic yielding in structures. So this wing structure, when you're sitting on the ground and you don't have lift on the aircraft, the wing structure is in this configuration. But in flight, when the aircraft is essentially being held up by the wing structure, the loads on it deflect elastically the wing up to this point. It's important that we design the structure so that is only elastic in its yielding. That is, we can recover the original shape when we take the load away. If we plastically deform this, we ruin the shape of the wing and the lift of the wing, and the airplane doesn't fly anymore. Fatigue failure, two of the most famous early examples of fatigue failure were the Liberty ships of World War II, where they had fatigue failures on the hulls, and the ships essentially broke in half and sank, many of them, with loss of life and lots of loss of very important materials that were headed for the war effort. This is the other famous example of fatigue. This is the de Havilland Comet. It's a British airplane. It was one of the first commercial jet airliners. And you notice in the stripe along the middle of the fuselage, the windows in the fuselage in the passenger compartment are square. That's as an interesting aesthetic for the aircraft, but this square corner on the window forms a geometric stress riser, and so they had fatigue cracks on the fuselage emanating from those square windows, and lost some aircraft because of that. Abrasion wear examples. This is a famous failure on Aloha Airlines. This was tracked back to corrosion due to inadequate maintenance. I believe this is a Boeing 737. But the pictures were so graphic when they got it back on the ground. This is immediately after landing, where the medical personnel are treating the surviving passengers. Several of the passengers were actually blown out of the aircraft when the skin came off. And it was the pilots were real heroes in this whole thing and bringing this thing back to ground. Thermal shock, fracture, melting, all these are common failure modes, not only in aerospace. This is the shuttle Columbia with the impact damage on its leading edge tiles, so that when it re-entered the atmosphere, this is from ice formation, breaking off and hitting the leading edge, so that when it hit the atmosphere, it broke up. Buckling, creep. This is a failure in a turbine. These turbines spin at very, very high RPMs, tremendous forces on them. And creep is a high temperature plastic deformation. So basically, when it reaches a certain temperature, it starts plastically deforming at an increasing rate, and at some point things collide at very high speeds. Aircraft failure modes and their breakdown. These are the instructor notes for the failure modes module. This module has 30 slides in it, so depending on how much depth you want to cover each of these failure modes, you could do this in one lecture period, 50-minute lecture period. You can cover the entire slide program if you're using this as sort of an introduction to the subject. If you wanted to go and use this as a more in-depth introduction for each of these failure mechanisms, such as deformation and fatigue, this could stretch into 2 lecture or even 3 lecture hours. So I'm going to quickly flip through these notes. Again, the notes are laid out with the slides so that each of the slides has this information that you can use to quickly go through and do your prep work, and also to expand the discussion for these slides. Student activities are built into this, so we have group activities and individual activities for students. Again, we could use this in class, or we could use this as external activities, or use a flipped format where you'd have the students go through the slideshow and perhaps extract out the instructor notes and give that to the students. They go through the slideshow and the instructor notes on their own, and then you do activities during the lecture period where you have all the students together. References. Nice set of references here, and that is failure modes. Aerospace materials quality control. This module, I think, is could be interesting to use in conjunction with a materials laboratory course. Of course, it could be used as an intro module, or an applications module broken up into separate segments and used as an applications material, not as a module together, in a quality control course. So this talks about the basics of quality control. The interesting thing is when we start getting into actual testing of structures in the manufacturing process. So we have liquid penetrant testing, which are things that we don't typically talk about in undergraduate engineering courses or technology courses. Radiographic testing, impulse and excitation, ultrasonics, acoustic emission testing. A lot of these are new. They continue to be developed and expanded in order to come up with new methodologies of looking at composite materials once you have them made. One of the issues with composite materials is you need a continuous structure, that is a structure that doesn't have voids in it when you put together the composite skins on things like airplanes. Voids can cause you real problems in delamination and all sorts of issues. And so you need to find those as early in the manufacturing process as possible so that you have the least amount of value added into the part when you have to scrap it. Positive materials identifications, laser and infrared testing, leak detection. This is something we don't normally talk about, but particularly when we're talking about building structures such as fuel tanks and buoyancy chambers in boats and that sort of thing. This becomes a real big issue. We talked about this in one of the other courses, one of the other modules that is, about embedding sensors into composite materials so that we end up with a smart composite. In the documentation, the instructor notes for the quality module, we have again a suggested presentation schedule. This material, my feeling is that I would probably either break it up into different segments and use the graphics and the information on the slides at appropriate times in a quality module, or I would use it as a single presentation, perhaps in a flipped type environment for a materials lab sequence. So again, we talk about each individual slide and give some background on this. And again, these materials are The notes are in Word, and the instructor presentation is in PowerPoint. And so you can break this up. You can use it as individual slides. You can use sections of it. You can mix and match fairly easily. Add material in or take material out. So we have some student activities down here somewhere. This is an interesting thing that I kind of skipped over when we were talking in the PowerPoint, is a list of standards that affect aircraft manufacturing. Standards play an important part in manufacturing, particularly manufacturing critical structures like airplanes. So we have ISO and we have mil specs for companies like Lockheed Martin and Boeing, Northrop Grumman. They live and die by mil specs. The aerospace quality standards, SAE, Society of Aerospace Engineers. Actually, that's the Society of Automotive Engineers, Aerospace section, I believe. And the AIA and NAS standards. And this goes everything from quality procedures to structure and quality of bolts, fasteners, and so on. So we have student activities, group activities, individual activities, and we have a pre and post test that you can take these test questions and stick them into either your testing or use them as a separate device. References, and that's it for quality.